This video addresses the stoichiometry of reactions between gases, as well as doing some additional problems with the gas laws. So when we have equations that have all gases, the stoichiometry becomes simplified. If the pressure and temperature are constant, the volume is directly related to the number of moles of gas. So we can substitute volume in for moles of gas in the equations, and the calculations can be a little bit simplified. So let's look at an example. Methane is a gas. You know this in your house is natural gas, and we burn it for heat and energy. So we have methane reacting with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water. We're used to reading equations and thinking of the coefficients in those balanced equations as moles. But since all gases behave the same, we can now start thinking about them as equal moles is equal volumes. So I can think of these coefficients as 1 liter and 2 liters, 1 liter and 2 liters here. So this allows me to write new stoichiometric factors. Previously, I wrote 1 mole of methane for 2 moles of oxygen, but now I can write 1 liter of methane reacts with 2 liters of oxygen. And I can do this to do some really simple stoichiometry problems. Let's look at an example. How many liters of oxygen are consumed by 4.5 liters of methane? Well, using this new idea with stoichiometric factors, I have 4.5 liters of methane, and I know from my balanced equation that 2 liters of oxygen will react with 1 liter of methane. And remember, these are exact numbers, so there's no significant figures here. So 4.5 times 2, we get 9.0 liters of oxygen. So if you don't know anything about the temperature and pressure, you can still do stoichiometry if you have something that has all gases. And this can be used to simplify calculations. Most of the time, if you forget how to do this, you can do it with another path using the ideal gas law. Now I want to look at a couple more problems that are sort of some advanced problems with the gas law. This one combines gas law information with stoichiometry in a more traditional kind of problem. So we have a gas collecting device in a laboratory that has a volume of 250 milliliters, and we're asked how many grams of sodium carbonate would be needed to prepare enough carbon dioxide to fill this bulb under the conditions 738 torr and 23 degrees C. Well, when you look at this, if you feel overwhelmed in reading, always start by making sure the equation is balanced, and this one is, it's 1-to-1-to-1 stoichiometry. Now we look at this, and we know that we made carbon dioxide. Carbon dioxide is a gas, so we can use the gas law, the ideal gas law, PV equals nRT, to talk about the carbon dioxide information. We know that we have a pressure of 738 torr. We know the temperature is 23 degrees Celsius, and we know the volume is 250 milliliters. Now, if we think about this, we could use this information to solve for the number of moles of carbon dioxide gas. So the moles is PV over RT. Then, once we have the moles of carbon dioxide, we can use that to find the moles of sodium carbonate, and from that we can find the grams of sodium carbonate. So that's sort of our path that we want to follow. Now we can go ahead and start plugging in the numbers. I changed the pressure into atmospheres. My 738 torr divided by 760 is 0.971 atmospheres. My 23 Celsius is 296 Kelvin. Always have to use Kelvin temperature. And my 250 milliliters is 0.250 liters. So now let's go ahead and plug in and find the moles of carbon dioxide. So it's equal to the pressure, 0.971 atmosphere, times the volume, 0.250 liters, divided by 0.0821 liter atmosphere per mole Kelvin times the Kelvin temperature, 296 Kelvin. And that gives us 0.00999 moles of carbon dioxide. So now I've done the gas law part of this problem. Now I can use the gas law part to go ahead and do the stoichiometry part of the problem. I have 0.00999 moles of carbon dioxide. I don't have to change grams to moles or milliliters to moles because I already have moles here. So now I look at my stoichiometric factor. I have 1 mole of sodium carbonate producing 1 mole of carbon dioxide. So my units of moles of carbon dioxide cancel. And I know that my sodium carbonate, 105.98924 grams of sodium carbonate, is 1 mole. So I get 1.06 grams of sodium carbonate. And now I have answered the question, how much sodium carbonate do I need to fill that bulb? So a lot of these problems use the ideal gas law to calculate the number of moles. And then once we know that information, we can go ahead and do something else with it. So as you look at these problems, the more complicated problems, we'll be using the ideal gas law, and then we go do something else. And a lot of times we're going to use these other concepts that we've discussed previously. And you even saw one example where we used empirical formulas. So go ahead now, and this is the end of this video, and you can watch the next video on partial pressure.